Hello, I'm Jay Whitacre. I'm a professor in two departments, material science and engineering and public policy. I'm also the director of the Carnegie Mellon Energy Institute, the Wilton E. Scott Institute for Energy Innovation. I came to CMU after working at the NASA Jet Propulsion Laboratory for 7 years. JPL was my dream job in many ways, and the choice to strike out from such a comfortable and prestigious position was something that was new and felt scary to me. But when I was there, I realized over a handful of years and many projects that while I was working for a bunch of amazing things up there, I was not working on things down here. And the problems that we have here are real. And they're just getting worse in some ways. But what mattered when I got here, and how can I make the biggest difference from the start, was the question that I asked myself. I was a material scientist, an electric chemist, and a power systems engineer. And I study energy storage, batteries, and how to make them work best in different settings. My key findings when I showed up and did this assessment were this. We are going to need a lot of batteries to get where we're going as a society. And to make use of renewable power sources like wind and solar, and to have cars that move us around without tailpipe emissions. We need to develop, make, and deploy a tremendous amount of storage. So the work I'm doing at CMU is focused not just on figuring out how to provide this amount of storage, but how to do it with the smallest amount of impact to the environment and society as possible. We must make sure that the solutions we are developing don't also generate more problems. Specifically, we're putting many more electric vehicles on the road in the next decade and beyond. Again, a lot. By 2030, many predict that the global annual electric vehicle production will be around 25 million. That's over 1,000 gigawatt hours of batteries and over 4.5 million metric tons of materials we have to make and transport around the world each year. It's a lot. The key ingredient in these batteries are the active materials, which look like black powders. But if you zoom way in, this is a high-resolution transmission electron micrograph. Material scientists love these kinds of things. These little fuzzy balls are actually atoms. They're metal atoms. And they're the key to what make this material work well. Most of these are common and cheap, except for cobalt. And this is a diagram of the structure, right? We have lithium, in this case nickel, manganese, cobalt, and oxygen. Of these, there's a problem player, and it's cobalt. We need it because the way it bonds with its neighbors results in just an environment that is just right for lithium to easily slip in and out of the structure during charging and discharging. It also provides good stability and safety for long-term use. This material is so important that this year's Nobel Prize in Chemistry was awarded to the team that first used lithium cobalt oxide in a lithium-ion battery. But it comes at a severe price. Beyond being the most costly constituent, there are substantial societal issues with this material. It turns out that nearly all the world's cobalt comes from the Democratic Republic of the Congo, a country plagued by civil unrest, poverty, and unfortunately, child labor practices. It's a sad fact of the battery industry. Many of the phones that you have, if they're Apples, there's good news and bad news. They have pledged to only use recycled cobalt in their phones, but a lot of it was probably initially sourced from this place. So, what am I doing? I'm working on new ways of producing and coding these fancy powers so they are cobalt-free and have rearranged atomic orders to compensate for this new crystalline environment. We're also looking at how to add other low-cost, environmentally benign additives that stabilize the structure in different ways. And we're also studying how new electrolyte materials can stabilize in the batteries so that we don't need cobalt, and in fact, things will work better without it than they ever did with. This work is complicated and ongoing. And another question is, what do we do about all the batteries that are already out there? They have these important materials. They're in battery packs that look like this. We have to figure out how to reuse them. Recycling, right? Turns out, though, because of the push to make the batteries so inexpensive initially, that recycling them is not very economically beneficial, right? So we have to use new methods to get the most value out. one of those things we want to do is refurbish the materials inside the batteries themselves. So harvest the materials, and instead of breaking them down to atomic constituents, keep them in that black powder format that we used, and reuse them in new batteries again. So this is another key project that's going on in my lab. So these projects, I hope I've communicated very briefly, they're complex. The questions that need to be answered come from fields ranging from quantum mechanics to supply chain economics. And the problems can't be identified and solved unless we all work together in new and exciting ways. And so this brings me to why CMU? You've heard this many times, I'll say it again. The scientists here are among the finest in the world, and we work across disciplines on projects to find solutions that are unexpected and would not happen without the kind of collaborations that we have and we practice here. And in doing so, I hope I'm convincing you we are trying to, and we indeed will, bring responsible and sustainable emerging technologies to the world. Thank you.